This is part 2 of hydrogeology, and this will be the last video lecture. So hang in there with me, please. So this time we're going to talk a little bit more about stream drainages, and we're going to talk a little bit more about groundwater in this video. So this is part 2, and so this will be the last one. So hang on. Here we go. You recall, as last time in the last video, we talked at the very close of that about drainage basins. We'd already talked about the patterns that streams make, and stream drainage patterns, but now we're going to talk about the kind of quality and the kind of quantity that comes out of drainage basins. And so, what defines a drainage basin is actually the divide. It's that sort of imaginary line that traces the outline of where water would strike the surface in that drainage basin and then flow from the tributaries, from the intermittent streams all the way into the trunk stream. And so that is a drainage basin, and it would be surrounded by other drainage basins, in fact. And recall also, not only can we have divides, but we can also have what are called interfluves, sort of wider areas. And so actually Springfield's pretty much an interfluve. I guess you could draw kind of a dash a line in, it's close to Division Street, in fact, in Springfield, where the divide is. So north of that, it goes into the Sauk River system. South of that, it goes into the James River system by way of a number of small creeks. And so really what we're talking about here is the ability for water to collect in these drainage basins, and then for scientists to be able to monitor it and to understand it. And so, in fact, that's the study of hydrology. Hydrology is the study of water resources and water quality. And it's both the subsurface and the groundwater hydrology that we're talking about here. So the hydrologists are the people who actually study that sort of thing. It's a very advanced degree. I guess you could consider yourself a hydrologist after you've got your master's degree in it. You have to study things like, we have to have a lot of calculus, actually, so Calc 1, Calc 2, Calc 3, and differential equations will get you a good head start on becoming a hydrologist. So hydrologists study flow. Also, computer sciences is really good for this as well. So if you study flow in the subsurface, you're usually using something that's mod flow, I think it is the name of the program. So anyway, hydrologists are these scientists who study water resources. Every single county government should have a hydrologist. I don't know that they do, but that's the sort of level that hydrology should be spread out amongst the municipalities and sort of governmental bodies, if you will. And the U.S. Geological Survey also has a host of hydrologists to keep their fingers on the pulse of the nation's water, to understand what's going on in the various systems and to protect those water systems, because that's the fresh water that we need to be able to drink. So from the headwater regions all the way down to the very limits, and so everything within that sort of region, that's the drainage basins we're talking about. And so in the United States Geological Survey, they divide up the river systems across the United States anyway. The USGS, with their hydrologists, they have to divide it up into manageable sort of areas. And so this is a map that shows you some of the subdivisions of the drainage basins. And so it's interesting. Let me put it that way. You guys already know that the Mississippi River drains much of the mid-continent area, but they've had to break that up into parts to make it manageable. And so what you'll see on this map is, in fact, the Caribbean is down here in Puerto Rico, right? Alaska has its own sort of area or branch, if you will, water resource region. Hawaii, its own as well. But if we look at the entire United States here, New England is separated off, the mid-Atlantic states, the South Gulf Coast, the South Atlantic states also have one. But notice in particular here, there's a lower Mississippi. And the lower Mississippi includes the eastern part of Arkansas, the westernmost part of Tennessee, and western part of Mississippi here, and almost all of Louisiana, but not all of it. So some of that is the Red River drainage. In fact, that's part of the Arkansas White Red regions here. And so that's a different region where they manage the resources in that vicinity. Right here in Springfield, we're right in between the Missouri River and the Arkansas White and Red River regions. So there's a lower Mississippi, there's an upper Mississippi. And as it turns out, okay, I don't know how much geography you've had, but the source of the Mississippi, I've actually waded across it. It's the outflow of a lake. It's called Lake Itasca. It's in northern Minnesota. But if you look for the source of the Missouri, you have to go a bit farther. So the Missouri is actually a longer river, but the Mississippi is the one that was, because it had more flow in it, it became the one that became the name bearer south of St. Louis, right? So that's the Mississippi River, but the Missouri flows into the Mississippi, and it flows, of course, across Missouri. It makes up the northwestern boundary of Missouri between Missouri and Kansas and Missouri and southeastern Nebraska. And it flows between Nebraska and Iowa, and it flows on the southeastern part of South Dakota. And then it flows through South Dakota all the way into North Dakota. And then it takes a left-hand turn and heads into Montana. And so the Missouri River, it's dammed up in a few places along the way. There's one major reservoir that's in western North Dakota, Lake Sakakawea. And beyond that, however, it's mostly a free river as I understand it. It goes past the town of Billings. It goes through a few more towns out there, but it's sparsely populated in Montana. And there's a place called Three Forks where three smaller rivers come together. Well, they're the tributaries for the Missouri River. So it's the Gallatin, the Jefferson, and one other one, which name escapes me right now. But that is the headwaters of the Missouri River, which is kind of neat. I saw that just a couple of years ago here. The first time I'd ever been to that place, but I've been to Three Rivers and seen where one and then two of them come together first, and then the third one within a mile or so comes into the same drainage basin. Beautiful place. So that's the Missouri drainage. And so you can see that even though there's water that's in the Missouri drainage, that's eventually going to wind up in the lower Mississippi down here. All of the water in the Arkansas White and Red River drainages are going to wind up in the lower Mississippi as well. Well, in fact, the Red River would flow all the way into the Mississippi, so they have to carve out and say, okay, this is what we're going to regard as the lower Mississippi River region here. And so you can see these are sort of manageable sort of areas for looking at water resources. So we're going to zoom in on this. In fact, we're going to zoom in on the south side of this mostly. And on this map, you can actually see the hydrologic units that they break it into. So for instance, each one of these is numbered, right? And so you can look at the White River here, and that is number 1101, okay? So that is the region. 1101 is the White River drainage basin. Now, the White River actually starts close to West Fork, Arkansas, I think it is, and it flows north just east of Fayetteville, and then it nips into Missouri, and then it heads back around out of Bull Shoals, and then it turns south again, and then it heads to the Mississippi River. But the hydrologic unit that they use to assess that river, it kind of stops once you get around Batesville. And so beyond Batesville, it becomes part of the lower Mississippi drainage, hydrologic unit then. Cats fighting in the distance here. I hope you appreciate that. This is the last video, so I'm not going to re-record this, okay? You can just listen to the cats. The Arkansas River, or Arkansas River, depends on where you're from, how you pronounce it. In Arkansas, they call it the Arkansas River. I think mostly in Oklahoma, they call it the Arkansas River as well. In Kansas, it's known as the Arkansas River, okay? And so I think even Colorado partially calls it the Arkansas River. And so the Arkansas River actually flows into the Mississippi River, of course, and it flows through Fort Smith, right? So Fort Smith, it flows through there, and then goes all the way into the mountains in the Rocky Mountains out here. It has its source a little bit south of Colorado Springs in that area, like Canyon City in that area. It's a little bit farther I think Salida, Colorado, may be one of the places that would be considered the headwaters for the Arkansas River or Arkansas River. The Red River, on the other hand, is the dividing line, the state line in between southern Oklahoma and northern Texas. And so that is sort of, well, you can see it on here. It's a state line. And so you can see where it meanders across there. So that's the Red River down here in the south. So the Arkansas is in the middle and the white is up in the northeastern corner of this hydrologic unit. If we zoom in even more, this shows you the White River Basin here, and it shows you some of the major lakes that we have. So even Heber Springs in Arkansas flows into the White River at one point. But in most of it, in fact, there are a few impoundments on it. So Beaver Dam is on here, Table Rock Dam, Bull Shoals, and then Norfolk Lake is on the North Fork of the White River, and it's been dammed up also. So Norfolk Lake is another impoundment. So 5 major impoundments in our region, one way up to the northeast there as well. It's a small impoundment. I don't even recall what lake that is. But this is the hydrologic unit, and I've placed on here the location of Springfield just to give you an idea. So on here you can actually see that's the James River that flows just south of Springfield there. And just south of the James, that's the Finley River, but both of those flow into the James River arm of Table Rock Lake. And so that is the subdivision for this area. You can get in even closer, okay? So this is the one that you can see Springfield shown on here, and that's the James River drainage basin here, essentially. So as they narrow it down, the codes become a little bit longer, okay? So you know that 1101 is the White River, 11010002, that's the James River drainage basin here. So they kind of arbitrarily cut it off and at the James River arm, where the James River arm runs into Table Rock Lake down here. But they've included some of the streams from the west, and I think that is, I used to know all of these because I used to kayak and canoe a lot. I think that is, name escapes me right now, but it's a pretty good kayak stream as I recall. And it flows I can't recall what it is, but I'll look it up. I'll give you a little annotation up here to show you what that drainage is that goes across Berry County down here into Stone County. So that's our local unit right here. And what do? Well, they have stream gauging stations on every one of these creeks practically. And in fact, you can go to the U.S. Geological Survey and type in, in the search string, you can just put in water, and it'll show you all the stations across the United States. Let me show you what this is important for. This is a snapshot of what it was like. I think it was in 2005 or 2004 here. But this shows you where there's been a fair amount of normal sort of rainfall and normal flow in the streams and everything, but there's a few of them that are particularly wet on here, especially like in eastern Colorado in that Arkansas drainage basin there, and then also along the Platte River. And that would have been, let's see, that was February of 2007. Okay, so that's the date on this map. And I'm guessing, okay, there was probably in February either a lot of snowmelt, okay, so that made those drainage basins higher than normal. Their flow rates would be a little bit higher than normal. Well, what is it based on is the question, right? So this is what it's based on. These are the stream gauging. It's clusters, actually, of stream gauging patterns. So in each one of these, I think that may be all of them, in fact, but all of them that were around in 2007 anyway. And so you can see where the wet areas are here. New record high. What that means is a new record stream height. Okay, so what that means also is it's going to have a higher discharge. When the stream height is high, the discharge is high. The blue ones put it into the 90th percentile, so that's pretty wet. And then normal is in the green, and then you get the dry areas. This is a snapshot taken when there was a drought in the southeast. It was one of the driest periods in the southeast, in Georgia, in Alabama, Tennessee, and so forth. It was just enormously dry right then. in 2007. So that's in fact the same year. It was just after we had the ice storm here in Springfield. So pretty interesting sort of time weather-wise. So if we look at some of the gauges in the Springfield area now, this shows you the South Fork, South Dry Fork, and so this is up on the north side of Springfield. And what you see here, now this is a different time period we're looking at here. You can actually see the dates at the bottom down here. So that's a week of precipitation in spring. Well, it's not the precipitation, it's the stream flow in the dry sock. And you can see that there's kind of a flat spot there. It was pretty dry. And then all of a sudden there was a rain event, right? And so there's a rain event and a big slug of water, that flash flood, in fact. So there was a small flash flood. Probably not very devastating. I don't recall what it was exactly, but those spikes indicate rain events. And so you get this sort of rain event. That would have been on the 20th of March. And you're looking at something that's about at noon. So this is divided into 24 hours, each one of these segments here. And so noon would be right in the middle of that. And midnight, of course, are the actual marked lines on here. And so you can see after that rain event, that slug of water that collected in the Dry Sock River, the North Dry Sock, South Dry Sock, it would have flowed out of that area pretty rapidly, in fact. So you can see the decline in flow through here. And if you look on the left-hand side, it's actually the discharge. So it's discharge over time over here. And so discharge on the left-hand side. So at the very peak, it was roughly 100 cubic feet per second. Okay, so you can think about that as being a stream that's 2-3 feet high and maybe 30 feet across. Okay, that's a good way to think about it. That's 90 square feet. And if you have 1 foot within 1 second, well, typically it flows a little faster than that. So if you flow like 3 feet per second, which is pretty common, that means you have to be 10 feet across and 3 feet deep and flow 3 feet down. So cube that out, and that's about 90 cubic feet. And so 100 is just a little bit more than that, not too much. So you can see where it declines, however. So there's a slight decline, and then there's another rain event. Oh, it looks like it's about 11 o'clock at night on March the 23rd here. And so there's another spike in this, right? So there's a double spike in the first one. There's a single spike in the second one. But it started from a higher base. And so, but the decline still comes along. So the headwaters in this area will drain out very rapidly. But they are prone to flash floods. Let's look at some more. This is this is Pearson Creek. Pearson Creek is a tributary of the James River, and it's just east of Springfield, in fact. I was out there tonight even. So it's a place where there are a lot of springs. And so if you have rain events on the Springfield Plateau, the water shows up at the springs, and you also get a lot of runoff as well. And so you could see that same double spike. There may have been one storm that overlapped, and very shortly after, 2 hours later, there's another storm that passes by. Well, that's very common in the springtime, right? In Missouri, we get a lot of rain in the spring, as you already know, this spring. So here's that double spike you can see again, and then it looks like there's a third, so it kind of takes a while to catch up. And that third spike is probably related to the spring flow, because Pearson Creek is the origins of Pearson Creek are close to, let me think of what that spring is here. Yeah, I'm losing my mind here, I think, this year. Jones Spring. It's Jones Spring. So Jones Spring would have taken a while for the water to finally get to Jones Spring, and then it flushes out. And so there's a little third hump on that curve on the left-hand side here. So that would have been, 10 o'clock in the morning here on March 21st here. And so if you follow that curve down here, there's that decline again, right? So you get a slug of water that comes in with a rain event. Then there's another rain event, right? And so the second rain event, you can see that spike roughly at 11 o'clock on the 23rd again. And then again, here's this sort of spring surge that comes after the rain event. And so Jones Spring actually collects a much larger area than just what is in that drainage basin, so it actually collects water from the north a little bit farther and a little bit farther to the east. There's a whole bunch of sinkholes in eastern Springfield, if you didn't know it. And those sinkholes, they collect water, and then it shows up over at Jones Spring, not too far away, maybe 3 miles away. So it takes a while for that to move that far. And so you can see that sort of second rounded sort of hump there that's not related to a storm event. It's related to the aftermath of that storm event that occurred on the 23rd. So that's the spring beginning to rise after that storm event. We look at a few more creeks around here. And so we're trying to evaluate what's going on, right? So this is Wilson's Creek. This is at Springfield. It is just, I think it's close to Battlefield Road. I'm not exactly sure where this gauging station is, but you can see here's that rain event again. This one's very spiky, right? So boom, it shoots up from only 5. It had 5 cubic feet per second, which is not much, right? So from 5 cubic feet, it went up to 900 cubic feet per second. That's a huge spike. And so, boom, all of a sudden, the Wilson's Creek is flooding almost. That's a flash flood right there. And as you look at it, it very steeply declines then again, right? And then there's the double spike on the 23rd again, right? So here's the first rainstorm, roughly a little bit before noon. Of course, it's on the south side of Springfield, right? So it would have gotten the water before the South Dry Sock actually received the same amount of rainfall. And so, boom, all of a sudden you get a spike there. And of course, rain is not always even with how much water it distributes across a landscape. You get the second rain event after that, then that looks like it's at about 8 o'clock at night there. And then it tapers off again. So that is what's happening at Wilson's Creek. And we're going to go one more station a little bit farther south on Wilson's Creek, and it is near Brookline. So this is a little bit south of Highway FF, I think. Yeah, it's a little bit it's before you get to what's the old Republic Road. If your a Republic Road runs out, that's where the Republic High School is, for instance, off of Republic Road there. I think it used to be Highway FF or F. And so that's pretty close to where the stream gauging station is. And here you can see a totally different pattern. It's a totally different pattern because you can see that it goes down, then it goes up, and then it goes down. Then you get that spike, and then it goes down again, and then there's another hump, and then another beginning of a hump, and then there's another spike there. The spikes are the rain events. Okay, those are the storms that pass through, the spring storms that pass through and drop a lot of rain on us. And you can see that at the highest output, the highest discharge on this, pretty close to 1,000 cubic feet per second. That's a lot. It's almost as much as it was. It was 900 at the other station farther upstream, right? But what are these little humps on here? You see the little activity, right? So it goes up and down and comes back down. Well, as it turns out, Wilson's Creek is captured for the Southwest Water Treatment Facility. They capture all the water so they can use it in treating Springfield sewage waste. It's a sanitary waste facility, and they try to clean it up there, right? So that's the one where you would actually spread the effluent across fields, let it dry out, and let it naturally be exposed to ultraviolet light, let it be oxidized. They spray it. They try to get all of the bad things out of that water, at sewage water. And it's a very complicated science, and the engineers who do this sort of work really do a service to mankind. And so each one of these sort of events, in fact, are discharge units. And so they discharge it over a long period of time. They treat it, and then they discharge it, and they treat it on a 24-hour basis here. And so you can see each one of those little humps in this diagram are related to those discharges. So one more to show you here. This is on the James River now. So this is going to be down, I think this is close to Kinzer Bridge here, but you can see the two spikes again here. And again, we're dealing with something, in this case, it's almost 2.5 times the flow of Wilson's Creek. 2,500 is roughly, this is a logarithmic scale too, I might point out. So logarithmic, in fact, is where you go up in small increments. It's a way to show a large variation in the kind of flow rates. And so when you see logarithmic, you can see that that second spike hits between the 2,000 and 3,000, or roughly 2,500. So that is the James River for the same time interval. The USGS does this. And so they do this in order to like warn people downstream if you have a storm event in one place. And upstream from that, well, downstream from that, you may have no rain whatsoever, but all of a sudden you're exposed to floodwaters. It's like, well, this explains why. And so they work in cooperation with the National Weather Service to warn people about like flash flood, events and things like that. So stream gauging information is pretty important. And so this slide just tells you a little bit about that. And there are several streams in the Springfield area, but not as many as you might expect. And part of that's because we live in an area that's pockmarked by sinkholes, and there are a lot of little small drainage basins that collect water and then discharge it out of springs elsewhere, maybe even in another drainage basin. So that's pretty common in Springfield, in fact. So you want to go down to Galloway Creek if you ever get a chance. There's 3 caves down there. There's one that's called Crawl All the Way, Walk All the Way, and then there's, I think it's called Sequiota Cave. And so those 3 caves are down there. Sequiota Spring flows out of one of them. In the old days, they used to take the Tunnel of Love, boat rides up that cave. And you could pole up the cave or paddle up the cave. And they stopped doing that after a while because people moved to the Galloway area and settled that area in the 1940s and 1950s. And most of those people were actually on sewage systems they're called septic tanks. And so septic tanks are where you get a giant concrete bunker with 2 chambers in it. And so on the first side of that bunker, it actually fills that, it has a basin that fills up with all of the solids. When I say solids, it's the stuff that comes out of us. And then the lighter stuff flows to the second tank. And so very slowly you can take all of those solids out. Well, on a regular basis, you should have your sewage system pumped out. Not too many people do that around here because it costs money. And so sewage systems are notoriously bad for overflowing and leaking. And so at Galloway Creek, that became a problem in the 1970s. It's rumored, in fact, that there were white pieces of paper floating out of that Sequiota Spring. There is even a school on the opposite, on the uplands over the top of Sequiota Spring. And in fact, when they sometimes do what they call dye tracing, and they can take a small packet of fluorescent dye, and they broke that open actually in a boy's urinal, and they flushed the urinal, and that dye went down the drain as a fluorescent sort of marker. It showed up in the creek. It showed up in the spring. And so there are leaky sewage systems everywhere in that area. At least there were at one time. It wasn't until about the year 2000 that they really kind of corrected that. And so every time a new development goes in, you have to be tied into the city sewer system. It's a way to funnel all of that waste and put it into the Southwest Treatment Plant. So just a little background for Missouri. Let me show you another one more of these. And now, by the way, these things are called hydrographs. Hydrographs meaning water graph, okay? And so this is on the Red River now. So we're looking on the opposite side of that management district. So this is on the south side, in between Oklahoma and Texas. And so this is at Burke Burnett, Texas here. And you can actually see a couple of rain events on July 3rd here. This would have been 2000, I think it was 2006, this one. I think it was a little earlier than the hydrographs I was showing you for Springfield here. But on here, you can see a rain event on the 3rd. You can see a rain event on July 4th, right around, just in the early afternoon here. And that's pretty common. The thunderstorms fire up, beginning at around noon, and then it rains in the afternoon. That's very common. And then it rained one evening on July the 5th. And you can see that it went from just over 100, there's 200 there, so about 120 cubic feet per second. All of a sudden it rose all the way up to 6,000 cubic feet per second. So 6 times more flow than what the James River had. And then you can see that this was a time when there was major flooding on the Red River, and that's the reason why I captured this, in fact. So if you look at it, it stayed high water for a long period of time, roughly, 1,200 it looks like here. No, 2,000, 3,000 cubic feet per second for the next 2 days, and then it shot up again to about 7,000 cubic feet per second. That's a lot. 7,000 cubic feet per second. So you're taking a 10-foot deep channel, 25 feet across, 30. Yeah, it's big. It's a lot of water flowing past a given point at a given period of time. Discharge, right? So that's off the chart, in fact, there. So the very top of the chart's 8,000 cubic feet per second. So we can do this pretty easily. Okay, so 20 times 20 is 400, right? So that's 400 cubic feet, 20 feet by 20 feet. So let's say it's 20 feet deep and 20 feet across. Well, that's 400, and you have to multiply that times 20. So 20 times wider, let's say. So, and then of course you have to multiply the distance, right? And so how far did it go? But 8,000 cubic feet per second is a lot, okay? So floods are a major problem in many places, anywhere where you have a river. Okay, so one little piece of advice for you: never build in the floodplain. Okay, if you build in a floodplain, you are at risk for flood damage, even in small creeks. Okay, so here's some people who built along the Napa River in California, and this is one particular year when they had a lot of flooding in Napa Valley. And of course, it puts people at risk and it puts property at risk as well. Well, it's cutting out the foundation from underneath of those buildings there. So flood risk is a major problem. And so the USGS is commissioned with that sort of task to try to understand long-term risks and short-term risks. In the grand scheme of things, how they describe floods, they'll often call it a 100-year event. And what that means is you don't periodically have a 100-year flood, or for that matter, a 500-year flood. That's the other sort of range. Or you could have a 1,000-year flood, which is an enormous amount of water, and you'd only expect one flood like that every 1,000 years. Let's talk about 100-year floods, because it's easier to put it into time context this way. Okay, so you have a 100-year flood 1 year because it rained a lot and you get floodwaters, right? Or, snow melts and you get a lot of flood water. And so that flows down the rivers, of course, in one big slug. And so eventually it's going to taper off like many of these hydrograph curves do. They have that sort of logarithmic decline in their discharge after a major flood event. But if you have a 100-year flood, does that mean that you're not going to have the next major flood until 100 years from then? There's no way to predict that, right? What they try to do is figure out the process stochastically. On average, you're only going to get one of those floods every 100 years. Well, you may have 2 of those within 5 years, or you may have 5 of them within 20 years, okay? So, it's kind of almost a misuse of terms, I would say, but you have to be able to partition that risk into some meaningful way to communicate information to the public. And so, yeah, this is a 100-year flood, or this is a 500-year flood. And it tells you the sort of magnitude of that flood water or the flood risk that we may be facing. And so, it helps us as a municipality to be able to understand the characteristics of the rivers around here. And I've already told you, in fact, that many of the rivers around here are flash flood prone. And so what that really means is they have a saying: if you drive along a road and you see water ahead of you, don't even try to figure out how deep it is. Turn around, don't drown. And that's there's a lot of force in water. I've already told you that it is 2,000 feet per For 1 cubic foot, that's 2,000 pounds of pressure that's added. Well, you take the size of an 18-inch tire, let's say, on a wheel, right? And you may think is like, well, I'm up high, I'm in my four-wheel drive. But remember, your four-wheel drive may weigh 4,000 pounds. I think mine weighs about 5,000 because it's an old truck and it's got a steel frame and steel bodywork on it. It's a 92 Ford long cab, right? But at the same time, it has wheels on it, right? And so those wheels have a cross-sectional area on them. I haven't tried to calculate it, but there's going to be more than 5,000 pounds of pressure if I tried to drive that truck into water that's 1.5 feet deep. In 1.5 feet of water, in my four-wheel drive Ford F-250 from 1992, that thing could still get washed off of a low water bridge. In the Ozarks, we have a lot of low water bridges. In other words, these are fords, really, is what they are, but they've been concreted in to keep them from washing out all the time. Well, in massive floods, they'll even wash out. And of course, with a low water bridge, where's the deep water? It's on the downstream side, right? So if you get washed off of a low water bridge, you're in pretty big trouble. On a regular basis, you can watch the evening news on television, any sort of like local news, and you can see somebody would have driven into water somewhere in this vicinity if we have major floods. You don't want people to do that, but it happens. And so with these sort of flash floods like this, our area is particularly prone to having people drive into the water and have to be rescued or maybe even lose their lives. So turn around, don't drown. Okay, so the other thing, of course, is if you have a major rain event and you have an impoundment upstream, that's another reason not to be living in a floodplain, because sometimes impoundments fail. Okay, so like for instance, both McDaniel Lake and the two closest lakes to us, McDaniel Lake and Fellows Lake, both have earthen embankments. They are covered by stone partially, but they're made out of dirt. And so that dirt, when it gets saturated, doesn't have the same strength that it would have had if it were dry and holding back the water. Lake Springfield, in fact, has a concrete spillway. Okay, so that they use that for the cooling. They used to use it for the cooling. Let me put it that way. For the old Southwest power plant. Actually, it's the old Southeast power plant. And so, so that is another thing to be concerned about with floods. So use common sense. In other words, watch the news. You can get a weather radio fairly inexpensive. Everybody's got a cell phone now. So just go to like weather.com. You can go to, there's a whole bunch of different apps you can get. So use those, okay? So don't drive in the country in rainy areas that are roads that you don't know, where there may be a stream that's over its banks. So get to high ground, I guess is what I would say too. Even in one of the major rain events that we had here, I have a basement in my house here, which is unusual in the Springfield area. Most people only have crawl spaces, but that basement actually had a 1/4 inch of water because our sump pump failed. So there's a lot of reasons you can get flooding with houses as well. So as it turns out, we talked about the major sort of events that have affected people on this planet. And it's always important to understand what the risks are, right? We talked about volcanic eruptions, and one volcanic eruption, for instance, killed 90,000 people. That was Mount Tambor in 1815, if you recall. And then there was that earthquake, right, in Tangshan. And when it occurred, there were 80,000 people, 800,000 people killed in that event. And so those are major catastrophes, okay? But by far, the worst human catastrophes that have ever happened are floods. Hurricanes can come and go. Tsunamis killed 250,000 people. 800,000 people is a lot for an earthquake sort of fatality, the fatality list there. In 1931, the Yellow River flooded in China, and it's the worst natural disaster ever recorded. They estimate that somewhere between 850,000 and more likely closer to 4 million people lost their lives in that flood. it floods on a regular basis. So the Yellow River, one of the major drainages that floods across the relatively flat areas of eastern China. 1887, the Yellow River flood is estimated to have killed somewhere between 900,000 and 2 million people. So, the population went up before 1931. So that is the story of surface water hydrology. We move on to the very last segment, and I think it's kind of appropriate actually, because the very last segment is about groundwater hydrology. And we're also going to talk a little bit about caves. We're going to talk about the karst in this area. So water does not pool in underground, not usually anyway. It's not usually in underground pools or underground streams. When in fact it does, it tends to get into fractures locally here. And some of that may be in caves and all, and some of it flows into other fractures then, right? And so eventually it may wind up in a spring if it's groundwater. Or it may keep infiltrating deeper and deeper and form part of the groundwater. And so, but it's mostly fracture porosity in this area. If we just look at the soil area, the upper part of the landscape, soils can contain water, that's soil moisture. And if it keeps raining and keeps raining, the soil moisture becomes saturated. All of the pore spaces fill up with water. And then if you have good permeability, which there's a little bit of permeability locally here, you can flow from one pore to another fairly easily. If you only have a tiny bit of water that comes in and rains, and then it stops raining, you typically have what they call an unsaturated zone within the soils. And so what you get instead is a mixture of air and water. And we already talked about water being a polar molecule, and it has a sort of plus side and a minus side. Well, what it does, it sticks to sand grains very easily, as you know, and it sticks to the surfaces of any solid surface, any solid material. So all the fractures would tend to fill with a little bit of water and then cling to the sides of that fracture. And in fact, that is that surface tension of water. And so, in fact, it's easy to pump out some of the water out of the subsurface. You can do it with a water well, right? So you bore a hole into the ground, it fills up with water laterally into that borehole, and then you have a pump that takes it up to the surface. That's a saturated zone, usually below the groundwater table, right? So there's a groundwater table down below the surface here where it's saturated. And the zone above that would be the unsaturated zone, right? So in between the two, there's a little zone. It's a little bit like a paper towel, but it's all based on that capillary action and also the surface tension of water. And so water will actually migrate kind of upward through the pore spaces, clinging to the sides and evaporating above it, right? And so the soil moisture eventually evaporates and some of the water flows downward into the groundwater. And so that's what people look for, in fact, in groundwater situations. This is a diagram from an old textbook that we used to use, and I think that it is not in our current textbook, but I think it's from our environmental geology textbook, Brooks Cole, I think. This shows you what it looks like in an unsaturated or undersaturated zone at the top up here. You can see the water clinging to these, they call them meniscus, and so the meniscus are these little pockets where the water will cling between the grains there. And then down below, you can see the saturated zone where all of the water has filled into that pore space. So the water table is actually right there in between the saturated and the unsaturated zone. That's a water table. And between, you get that small area of capillary action going on, or the capillary fringe, they call it here. But that's your water table. At the very top, there's a little tiny bit of soil moisture that would be a residue from the last rainstorm, perhaps. So if you were to project that into a drainage basin, let's say, and there's a river at the bottom of this drainage basin, that water table actually has a tendency to mirror the surface topography, and then it would flow downhill even in the subsurface, right? Because there's that potential of being pulled by gravity into a lower state. And so eventually the water will flow downward, even in the subsurface, from pore to pore, in a porous and permeable medium. And so here you can see in the diagram directly below the upper left here, you can actually see where the surface there has a river flowing through it, and then the water table kind of mirrors that surface. And you can see also where the water table can drop if you have a drought. And so the water table very commonly drops where you have a drought. Well, why does it drop? Well, it's because people have wells, and then also some of the water is in connection with that stream. And so they show you that situation at the top diagram up here where there's groundwater actually flowing into a stream here. That's called a gaining stream. So a gaining stream is where there's an excess of water flowing in from the groundwater into a surface water stream. Sometimes in semi-arid and arid areas where there's a river flowing through it, the water actually percolates into the stream bed and flows into the subsurface, into the groundwater. And it's what they don't have a name for that really, but it's a losing stream is one of the terms that we use. So in a losing stream, you actually have a net loss of water from that stream into the unsaturated zone, and making the saturated zone fill up with more water, I guess I would say. At the very bottom down here, they're saying it's a losing stream also, but it's one in which the water table has dropped so dramatically that the water flows directly from that stream bed all the way down to the water table in order to try to replenish the water. So there's some terms we're going to put on to this as well. Whenever you have a rain event, you're actually giving it a recharge. And so it's like recharging a battery. Well, you're recharging the water in this case. And so the recharge area, for instance, in the Springfield area is mostly east of here, and then also the surface water. So in fact, we have two aquifers in this area. Now, aquifers are areas where the groundwater is kind of perched, if you will. So there's a surface aquifer in Springfield. That's called the Springfield Aquifer. And then if you get through what's called a confining layer, you're in a lower aquifer there, and that's called the Ozark Aquifer. And so two different aquifers in the Springfield area, and both of them have pretty good water for the most part, but the upper aquifer is more prone to being polluted. And the reason for that, of course, is it's a direct connection with the surface, right? And so anything that happens at the surface is going to get into the groundwater. So groundwater hydrology is pretty important, especially in the Springfield area, because we have limestone around here. And we have a phenomena where we have a lot of caves, we have a lot of springs, we have a lot of sinkholes. And in fact, many of these sinkholes are actually connected to caves, and those caves are actually connected to springs as well. And so water flows in the underground around here like crazy, and it follows fractures. It will actually cause those fractures to widen through time because it dissolves the limestone. Rainwater, as it turns out, is slightly acidic, and it will actually eat into the limestone. And so if you ever drive down the highway, you can actually see the road cuts where they've been weathered at the top, and they leave behind a clay and chert residue at the very top of the rocks around here. But in fact, the limestone itself is being disintegrated like a pile of sugar in the rain, right? And so it's not quite as fast as that, but it is happening at a slow pace. And so those ions actually get into the fresh water around here. We have very hard water in the Springfield area because we have a lot of calcium, we have a lot of magnesium in it from the dissolution of the limestones and dolomite around here. So if you can imagine, if you can pull out water out of the subsurface, out of that saturated zone below the water table, right, you can actually pump out a lot of that water. But there's a certain part that you can't pump out because it's stuck to the grains or stuck to the fractures. They call that specific retention, the amount of water that you can actually pull out of the subsurface in a pump test. And then the specific yield is the amount of water that you can actually move through the rock and pull it out. And so specific yield and specific retention generally are from pump tests into aquifers to test the viability for those rocks to contain fresh, potable water for drinking. And so permeability is a major factor in this, right? So permeability is the capacity for an aquifer. Now, there's a little parallel between aquifers and petroleum reservoirs. Petroleum reservoirs are full of oil and gas, but aquifers are full of water. typically it is fresh water. Okay, so fresh water is what we can use, and so those are the aquifers that are handy for us. If you have a saltwater aquifer, what good is it, is the other point. You can't irrigate with it, you can't drink it, right? So you'd have to desalinize it in order to use it. There are places that do that, however, but it's better to have a good freshwater aquifer. So permeability is important, porosity is really important. The highest porosity you can really pretty much get is about 30%. That's when you're stacking grains very carefully and you get really large pore spaces. But, or if you have a cave, my gosh, you're going to have a lot of porosity if you have a cave. So cavernous porosity or fracture porosity can give you a large percentage of porosity as well. Permeability, we measure that with a rock unit called Darcy, but most of the calculations that are based off of how you can drain water out of an aquifer based on the permeability. You can do tests on it for one thing. They do what they call a capillary pore pressure test. They do it with, as it turns out, a liquid metal. Okay, so they inject it with mercury in order to see how the mercury can penetrate into the pore spaces, and then how it drains out and so forth, and how connected are they. And so it's easier to force a lot of pressure on that mercury in order to get it to penetrate into a rock sample. They usually take little tiny cores to be able to do a mercury capillary pore pressure test. But it's not all that commonly used. They use it more, in fact, in the petroleum industry to figure out the porosity in a petroleum reservoir. But for general reasons, they usually do pump tests and for aquifers, because it's a good way to test. It's a good way to test. So low permeability rocks are not very useful either, even though they may have a high percentage of porosity. Like shales very commonly have a pretty good porosity. Let's say 2-3%, sometimes 2% anyway. They don't work where you get the pore spaces that are able to communicate with one another very commonly, because of course shales have been compacted. They've been squeezed, if you will, and dewatered somewhat, so it's squeezed most of the water out already. Those shale layers are a lot like in petroleum, where we talked about seals. And so seals are impermeable rocks, very commonly shale. A shale that has water in it, perhaps even. And so those low permeability rocks, that's a confining layer, we call it. They used to use a term called aquitard in the old days. And so you'd have an aquifer with an aquitard and then another aquifer. I don't know, it's kind of a crazy term. In other words, it's retarding the flow of water in between two aquifers. Really, confining layer is a much more appropriate term to use these days. And so confining layers are what we're going to call those layers that are impermeable. Shales, for instance. So in the Springfield area, I've already told you we have two aquifers here. We have the Springfield aquifer at the top, and then we have the Ozark aquifer down below that. In between, there's a confining layer. And that confining layer is actually called the Northview Formation. The Northview Formation is made out of clay. It's a clay stone and a siltstone. And it's actually what we put the sanitary landfill in. It's about 60 feet thick out there. And then you line that material, that Northview shale, the Northview Formation, and you line it with a 60 mil polyurethane liner, and they can seal it and weld it, so it becomes impermeable also within an impermeable rock. And so it's a good place to store waste, essentially. But it's also good for protecting the water that's down below that confining layer. So I'm going to give you one more example of a freshwater aquifer that's currently at risk. There's actually a book written about this. It's called Ogallala Blue. And so the Ogallala Formation crops out in a few places in West Texas. I've seen it out in the field in places like Palo Duro Canyon. It's a conglomerate. And so it's a conglomerate that actually recorded the uplift and weathering of the Rocky Mountains, the front range of the Rocky Mountains. And so if you look on the map on the left-hand side of this diagram, you can actually see where the Ogallala Formation was deposited. Now, they give it a blue color because it's been a very good aquifer for a long period of time. But today, parts of it are completely depleted, especially in West Texas, in the panhandle of Texas, in an area called the Llano Escotado. staked plains, it is an area where they've overpumped it by irrigating the land, right? And so you irrigate it, or you have too many water wells in that vicinity. And if it's not very deep down to that aquifer, and if it's not getting recharged, you can overuse it, and the next thing you know, that aquifer is going to go dry. And if you ever have a chance to fly to Denver, it's one of the major airport hubs that you have to fly through, especially if you fly out of Springfield. And when you fly over western Kansas, you're going to see what look like crop circles. That's what most people call them. They're actually pivots, and there'll be fields of oats or alfalfa or wheat or corn. They even grow corn that way, and even sunflowers actually in Kansas. And so they use the Ogallala Aquifer as the source for the water for each of these pivots. So they have a central part that has a sprayer, and the whole thing is driven by wheels, right? And so the whole thing spins around in order to irrigate the land. Well, it's very productive land as long as you have water. If you don't have water to irrigate with, you're not going to be able to raise crops. It's a major issue out there, in fact. So water rights are a big problem in the West. In fact, if you want a good career that does community service, being a water specialist, in fact, even a water lawyer, I would say, if you're an attorney for water rights, that's one of the major concerns for people in the West. They passed a law recently where you cannot collect rainwater in places in Colorado. Now imagine that. Water falls on your roof, falls into your gutters, and you cannot collect it into barrels because that water belongs to somebody else. That's on your house, okay? And so in the subsurface, you can't put a well in without permission in some places, okay? So there are places where you have to use municipal water, in other words. So there may be a municipal well that has been permitted, but you can't put in a personal well. So that is one of the major aquifers in the high plains of the United States in central North America that is at risk for becoming a depleted aquifer. I think it's about half gone in some places. If you look over here on the right-hand side, it gives you an idea of a different kind of irrigation. So if you look at the top up here, it shows you there's a well at this one farm over here, and then there are two other wells that are there as well. And you may have livestock or whatever that you can feed off of a stock tank, and you may have one of the spinny type of windmills. Okay, so they run around like this. Metal windmills in western Texas, all across the high plains, are really common. They're usually broken, okay, but they're there for a while. But then when you get a tornado that comes through, 100-mile-an-hour winds sometimes, and they'll break those things. But they're set up to be able to be to be an energy-free sort of system, essentially, by pumping water out with the use of wind power. So there's well number 1, well number 2, and well number 3 up there. And what they did with well number 2 in the middle there, you can see that they hooked up a irrigation device to that, and that's called a wheel line, that variety. And so there's a whole series of wheels, and it rolls across the landscape in a linear fashion rather than pivoting in a circle. But it's the same concept. You have to have a well hooked up to that wheel line in order to irrigate the crops. Very common with like raising alfalfa. And so that wheel line cuts across, and it uses that water, right? So it sprays the water on the surface. That water eventually is going to infiltrate into the soil, but some of it, the wind out there, and we're talking about high plains now, in the high plains, you're going to lose a lot just to the wind coming along and evaporating that water away before it's of any use to that plant whatsoever. So they like to use drip irrigation if they can, or sometimes they use end guns on these pivots, and sometimes they use sprayers, but drip irrigation is actually the best way to go for most of this, but it doesn't usually deliver enough water for the types of crops that people want to raise. They want to get high yields, right? So you have to use water in order to get high yields. They're not used to dry land farming yet. They will be one day, okay, and I can guarantee you that. They've used so much of that water in that wheel line in the lower of those two block diagrams that, in fact, if you've ever drank a milkshake before, and you're drinking that milkshake, and you get down to the bottom and you can see the milkshake flowing into that straw, And that's the same sort of idea, right? So the well is that straw that's sucking out the water, and you get what they call a cone of depression. So in a milkshake, it's kind of like shaped like a cone, right? A cone that's draining into your straw. And so that's a cone of depression right there. They pumped so much surface water in this lower block diagram that they've taken the water table below the well that serves that household over here. And so that well's gone dry now because it's taken it from the saturated zone and it's made that into an unsaturated zone now. And you can't pump out of an unsaturated zone. That well has to be in the saturated zone in order to produce water, to have a specific yield, in other words. It may have some specific retention, but that's not enough water to flow into the borehole for that well. And so the well itself would go dry in that case. The other well went dry as well because the water table dropped. That's an issue around here. During droughts and times like that, you can actually drop the water table around here. So people are concerned about how much rain and how much recharge there is to many of the well systems around here. I'm going to show you one more example of a different kind of hydrological system. And this is actually called it's an Artesian system. And so it combines like a recharge area that's at high elevation and then a place where it's used at low elevation. In fact, if you can imagine recharging a rock unit, let's say it's a sandstone, for instance, that sandstone fills up with water and it begins to flow downward in that aquifer because of force of gravity, right? And gravity takes it farther and farther down, and it flows into the subsurface below, in fact, maybe an agricultural area like the last one we were looking at. And so here's a well that they show you here. There's two wells on here. There's a well number 1 in the top block diagram, and then well number 2. And then down below that, you can actually see a close-up cross-section of that area. So you can see where the recharge area is and the water flows in there. And if you have a well up in the mountains there or in the foothills just below that, you'd have to drill into that rock layer that is full and saturated down there, but you'd have to pump it out of there, because it won't flow to the surface all by itself. But if you follow the pressure that is at the top of that aquifer, if you're to trace out where the water level should be by all rights, it's actually up in the air. And so for well number 2, in fact, that pressure surface would allow water to actually flow at the surface. And that's called an Artesian system. You can see the terms aquifer and aquitard on this. So where it says aquitard, replace that with confining layer, okay? So where it flows out at the surface like this, remember it's the pressure surface that's more important and where the recharge is located. And so if that recharge is at high elevation and your well is at low elevation, it could actually become an artesian well, and you wouldn't have to expend energy in order to pump it out at the surface. That's an Artesian system right here. We use the same principle for our water here in Springfield. In fact, every municipality does the same thing. Who hasn't driven down the interstate or at least seen water towers in every little town that has municipal water? And so one of my favorites, in fact, is Bourbon, Missouri. They have 2 water towers there, and one of them's leaning over as though it's been drinking bourbon, but the other one is right next to it there. And so they're both water towers. And so what we do is we pump the water into that tower, and then in any house that's below the surface of the water in that tower, all you have to do is turn the spigot on, and the pressure inside of that water tank will force the water through the water lines to your house, in fact. So all you have is a valve that will open up that flow. And so that you don't want to leave the water running because they charge you for it, right? So there are gauges on all the houses, right? But at the same time, it's like in your house, you don't have a water pump in order to get water to distribute to the toilets and things like that, right? I think the only place we have a toilet in the downstairs in the basement, right? And that's hooked up to a pump in order to pump it up, okay, to get it out of the system and into the sewage system. But you don't have a water pump. That's because water tanks give us that artificial pressure surface, or that they call a potentiometric surface up high, up above many of the structures. If you have a large building in the Springfield area, many of those actually have water tanks, and so they have pumps that will take the water up to the top of the high buildings in order to distribute the water down then. And so that is an example. They call that process where you have a pressure surface, that's called hydraulic head. Hydraulic head, so you have pressure up high that pushes the fluid down lower. And so hydraulic head and that pressure surface, or potentiometric surface. So just a few more concepts to mention to you. One of those is if you overuse a freshwater aquifer, it can become disastrous if you live in a coastal setting, because if you pump out too much water, the salt water could actually infiltrate through the beach, through the sea floor, into that freshwater aquifer. Has that happened before? It happens everywhere that's close to the ocean. I talked to my friend from Amsterdam, from Rotterdam, and he says, "Oh, it's a big problem there. Do we have saltwater intrusion?" And he's a water expert. He's a hydrologist, and he says, "Yeah, saltwater intrusion, subsidence. These are all problems that they have there." So what happens, in fact, is when you pump the fresh water out, the salt water gets a chance to then flow inward, and so this diagram here is not the groundwater, but it's the actual amount of rain that falls in California. And so the average annual rainfall is less than 5 inches in the deserts, right? So under 5 inches for the orange parts on here, the light orange, 5 to 10 inches in the LA Basin, which is down here. It's in yellow down here. You can see the Channel Islands off the coast there. So one of the Channel Islands down here to the south, I think that's San Clemente there. It's in the yellow, and so it only gets 10 to 15 inches of rain a year. Well, we get closer to somewhere between 40 and 60 inches here in Springfield. We're much wetter than what they are there. We're much wetter here than they are in western Kansas. There's a steep gradient. As soon as you get to the state line, practically, the amount of water or rainfall drops off by about 20 inches. By the time you get to the 100th parallel, you're getting maybe 10 inches out there, 10 to 15 inches out there. So it's a lot like LA. So if LA doesn't have much water, where do they get their water from? Well, some of it's from well water. They have a subsurface aquifer there that they can produce water out of. And a forward-looking, forward-thinking sort of person back in the 1930s, his name was Mulholland. And so Mulholland actually stole water from Northern California. He built what they call the California Aqueduct, and he took that water out of Northern California, Owens Valley, in fact. He took it out of Mono Lake. We talked about Mono Lake when we talked about Mono Crater and the Mono eruptions from the Bishop Tuff and everything, right? That's Owens Valley, and it's just a little bit west of Death Valley. And so it's a valley where they could pipe that water, or even better yet, have it flow across the surface on an aqueduct, and you could deliver it to Southern California. So Mulholland made a lot of money off of that project. And all of a sudden, Southern California and the LA area went from being an agricultural area to be a booming city. And today there's 20 million people that live in that basin, in that LA Basin sort of area. So it's kind of nestled in the mountains, if you will. 20 million people using water on a daily basis, right? They sometimes have to ration the water in order to conserve it. And they will fine you if you're watering on the wrong day. So if you have some drought conditions, they will make sure that you only water on uneven days or odd days. But saltwater intrusion is one of the major problems they have here. So you can't take all the water. In fact, they passed restrictions on how much water they could actually take from Mono Lake. So instead, they're pumping out of the subsurface, right? Here's an example of that, in fact, and this is a diagram that I drew for the U.S. Geological Survey. I worked on a project on saltwater intrusion back in the late 1990s and early 2000s. And so this is a diagram that shows you a confining layer right at the surface up here, but the aquifers down below that. And normally you would have a well that would produce fresh water out of that aquifer. You begin pumping it out like a cone of depression, except this time it's that potentiometric surface that begins to have a depression, like a cone of depression in a well. And it draws down, so that cone of depression develops, and they use more and more water out of that for municipal uses, industrial uses, commercial uses. There's a wedge of salt water that can actually infiltrate. And what they found in the LA Basin was that some of their wells were becoming salty. Now, here's the issue. If you took a 2-liter bottle of water and you took the cap off, and then you got a little salt water, and you added that salt water, the whole thing's going to taste salty. It doesn't take much salt water in order for water to taste salty. People don't like to drink salt water, and salt water is actually bad for you too. It can cause your cells, of course, to kind of like stop having osmosis, I think it is. So it's bad for your biology, in other words, and it's bad for people who have heart problems too, I think, because they're supposed to be on low sodium diets, right? So if you're drinking salt water, that's not a good thing. So salt water is an issue, right? So how are you going to stop the salt water from intruding? Well, one of the ways that they do that is they drill another well that's closer to where that salt water is actually intruding, and then you have to use some of the water in order to like build a curtain. So they build a curtain essentially of pressure, and they try to stem the flow of that salt water so it doesn't infiltrate into that fresh water. They did that in the LA Basin for a long period of time. Alameda has some of these. There's some on the El Segundo side where there's a barrier as well. There's a whole series of injection wells, and so those injection wells take the very purest, the very cleanest water because they don't want to inject dirty water into the subsurface, and so they take the very best water and inject it, and you can't even use it. In fact, if all it does is it holds back the salt water that way. It's a very clever idea, but at the same time, it's very costly for how water is used. There's too many people in California to begin with, right? 20 million people living in that area is a lot. Yeah, the barriers help a little bit, but they found that they weren't always effective. And the reason they weren't effective is because they didn't take into account the sedimentary succession there and what the stratigraphy was like. And as it turns out, many of the flow paths for the salt water weren't just directly in from the seafloor. They were following things like ancient river channels that had flowed across that landscape. It'll get into that river channel and flow backwards because there's a negative pressure back here. Well, somebody's sucking on the straw back here, and it sucks that salt water right in. And it was ducking through some of these wells in that barrier. Pretty big issue. They hired the USGS to come in and try to solve that problem. USGS went out and we did surveys, seismic surveys, as best we could anyway, and then took drill core across this landscape in order to try to figure out what the stratigraphy really was there. So saltwater intrusion, a major issue, not just in LA. Okay, it's in Northern Europe as well, the flatlands of Northern Europe. Oh my gosh, think about the deserts, right? So all of, Egypt, all of Israel, Greece, there's, you name it. It's any one of these nations that have cities right next to the ocean where they're using groundwater for a source of drinking water. It's a problem. Saltwater intrusion. Maybe you don't hear much about it, but South Africa, African coast in general, or anywhere where you're close to a desert perhaps or a semi-arid area. South America even. So everywhere you can imagine pretty much has a saltwater intrusion problem. Yeah, so it's an issue. Another issue for us locally here, we've already talked about pollution. I won't dwell on it too much, but here when you put something into a sinkhole or if you put it on the land surface and it's a contaminant, it will get into the freshwater subsurface groundwater. It'll get below the water table and then it will contaminate it. So that's an issue for us here. Here you can see actually the pockmarked landscape that develops in a karst terrain. So they call it karst. Karst is actually a Slovenian term. Now, Slovenia is a country in the Adriatic Sea, a little bit east of Italy. And it's loaded with sinkholes in that area. And the sinkholes, the caves, the springs, those are all common features that you see in karst. I like to compare karst in the Springfield Plateau a lot to like a sponge. You can drop a little bit of water out, immediately it sucks that water right in. That's why we don't have any big streams that run through Springfield. We're not the river city here, okay? So the James River actually gets down to where it's flowing on top of that confining layer, for most of it anyway. So that's one of the reasons why the James River Valley is there. So it's on the north view in a few places anyway. So this is kind of a snapshot of what it looks like in the Springfield area. You get springs, caves, karst, and sinkhole collapses like this. And the water table, of course, is also going to be here. It's just that it's more prone to being having higher fluctuations because as people use it out of the subsurface, it goes pretty fast, right? So there's not a pore-to-pore connection usually with the solid rocks around here. It usually has to flow through fractures, and fractures are no good at all for trying to filter the water as it goes out. If you're in a place that has a lot of sand, sand is pretty good as being a filter, okay? But here, where it's all limestone, not so much. Yeah, so Springfield, Greene County, more than 350 known caves and sinkholes in Greene County. I think there's a lot more than that, in fact, a lot more, okay? We have some famous caves in this area too, right? You know, there are tourist caves, there are a lot of other caves in this area, and I just mentioned the ones down at Sequiota Park, so you might want to visit those at some time. So if you dissolve caves out, and that's what causes, that is a karst product, essentially, is the dissolution of limestone. How do you dissolve it? Well, when you had, okay, let's start from the beginning, okay? So limestone is made out of calcite. Calcite dissolves in the presence of dilute hydrochloric acid. Well, we're not exposing these caves to dilute hydrochloric acid. We're exposing it to humic acid, which forms when rain and groundwater flow through leaves, and the leaves pick up humic acid. And so the humic acid may have a very slight acidity to it, but it's enough to make out huge rooms in some of these caverns around here. So you have a cavern that opens up, let's say. Some of it may be below water, some of it may be above water. And they call that phreatic, and then there's also the Vadose Zone. So the Vadose Zone is above and the phreatic below. Let me draw an analogy for you. The Vadose Zone is a lot like the unsaturated zone in soils that have pores that connect them. The phreatic zone is where the water has actually flowed through that cave, perhaps. And so phreatic has something in conjunction with the water table, let's say. But the water table fluctuates, right? So if the water table fluctuates, sometimes it's phreatic and sometimes it's not. So many of these caves, in fact, in the Springfield area, have been phreatic at one time or another, but today they may have a vadose zone in them because the water table has dropped. So once you drop that water table and you dissolve the limestone from above, what you get on the inside, because it's an area that has a special sort of microclimate, you can actually reprecipitate some of that carbonate down there. And that's what you see here. Those are speleothems. Some people call them cave formations, but we use the term formation in a different sense, as you well know now. A formation's a mappable rock unit, so we call these cave features speleothems. And the study of caves, in fact, is called speleology. So we offer a course in that, actually. So speleology is one of the courses that would be handy to have for somebody who is in environmental science, just so you can understand kind of the water flow in this area. So these are speleothems in a cave right here. So how do we stop groundwater contamination? Well, you pass laws. You get people from dumping things. You have to educate people first. You have to tell them that what you dump is going to come back sometime to haunt us. I can guarantee you that, okay? There are places, we've had Superfund sites in Greene County related to Union Carbide. There's a Union Carbide plant here that was a Superfund site. Now, Superfund means that the companies were fined and that money goes into the rehabilitation of that land, where they try to make sure that they can actually clean it up, okay? So the USGS is one of the agencies that monitors those sort of places, that looks at the water resources and so forth. Also, the EPA, the Environmental Protection Agency, is good to monitor wastewater. I know that in the city of Springfield, when we have flash floods, very commonly, that we have sewage releases out of the Southwest Treatment Plant, and we get fined for that, like $50,000 a day for every day that we overflow some of the sewage treatment. That's when the Wilson's Creek actually gets out of its confines, essentially, in the treatment facility, and it overwhelms the treatment plant. So it's an issue. It's an issue. We also have to raise awareness. That's the number one thing. It's like, don't dump your oil on the ground. That's crazy. Don't dump anything on the ground. Maybe water your plants, okay, if it looks like they need watering. But if they don't need watering, don't use water on the ground either. Yeah, it's a precious resource. And as you know, there's not that much fresh water. So we have to kind of guard it. We have to safeguard our resources, because you know how, maybe you've got some friends, maybe somebody's told you this before. It's like, you're your own worst enemy. And that can be the case very commonly with places where there's bad practices, where there's a bad culture, or maybe where there's just not enough education so that people understand that what they're doing is going to be damaging in the long run and not good for their children and not good for their grandchildren. So that's one of the issues we face in Springfield, is the karst topography that's here and the disposal of wastewater in general. And where does it go? And it's a major issue. And this pretty much wraps up this course. You only have the final left to take, and maybe the lab final. So this is the last week of classes, and in fact, the last day of classes is just 2 days from now. So, or 1 day from now. Actually, tomorrow is the last day of class on Thursday. So I'm going to try to get this thing It takes 10 hours for this thing to get rendered, and then I put it in another one, then it takes another 3 hours to render. Yeah, it's kind of been a tough semester. Just keeping up with this course. I really like the fact that I was able to record these things, however, because I feel like I should have been recording them all along, perhaps anyway. I think I've got important things to say, and I think it's a very important part of your education to understand geology. I hope you feel that way, actually, and I hope you really learned something out of this course. I hope the videos were of some help. Normally, this would be delivered all in person, and it's much more interactive, and I get to know your name, and you get to know who I am, and my personality. It takes a while for it to come out, but here it is. I'm excited by this stuff. That's my profession. It's what I love to do. I love to teach about it too. I love to share the information that I've gained over the years and the experience that I've had. It's not been a good semester, but it's not been a bad semester either, for that matter. So I hope that you've stayed healthy. I hope that you get your injections. That's really important. If you come back in the fall, and I really strongly encourage you to do that, if you're really interested in geology, the next step along the way would be to sign up, register for Geology 314. It is historical geology. That's the second in the line of courses for geology. We usually get students to take that and mineralogy at the same time to save some time in the long run if you take geology. It's an interesting field. It's taken me around the world. I've been to Antarctica 3 times. I've been to the Arctic Circle working on geology in northern Alaska. I've got to visit places in Scandinavia. I've been to Thailand. I've been to New Zealand. So if you like to travel, geology is a good ticket to do that. Every national park that we have pretty much focuses on the geology. So they're really special places, and a lot of people agree with that, that we really need to understand geology in order to understand and make this a better world. Geologists also have a certain sort of capacity. Most of what you've learned this semester is about the processes involved, like plate tectonics and how minerals form and how rocks form and how sedimentary rocks form and how rivers flow. We didn't learn a lot about the ocean. That would be another aspect, and coastal geology is another aspect that I would have liked to have talked about, or glaciers is another one. We did talk about climate change. We talked about energy resources. We talked about geologic structures. Wow, there's a lot of stuff that we cover in here, but in the grand scheme of things, I hope you retain it as much as you can anyway, because it may impact your life later on. In fact, where you live, where you build a house, if you build a house, or if you live in an already established neighborhood, if you live in an apartment complex, if you live in a city that's prone to seismic events, so this is going to be one of those ways to protect yourself and your family. Anyway, thanks for participating in this experiment. It really has been an experiment, but I think it's meaningful for me to have gone through this exercise, to be able to share with you a knowledge, and now it can be out there for everybody on YouTube. And not that I have very many subscribers to my channel. I don't care if I do or not. I'm not trying to monetize this. I'm just trying to share information. So anyway, have a good rest of the semester after the final. The final is going to be May 12th. It's going to open up at 8:45. It'll close at 10 p.m. on that Wednesday. It's going to cover everything that we've covered. It's a comprehensive exam, but half of it is going to be off of everything that we've had for the last 3 weeks, I guess it is, ever since we had the last exam, okay? So the last exam, I don't remember even when it was, but every lecture that we've had since then, every video since then, every presentation in PDF format, you can go through those and look at the videos. Anyway, thanks a lot for your help, and thanks for hanging in with me and making this the best of all possible worlds. That's out of Voltaire. If you ever get a chance, read Voltaire, read Candide, okay? That's one of the books that he talks about. Yeah, thanks a lot. And I'll be teaching historical next year, so if you're interested, come on, take that course. Even if you're not a geologist, you might really like it, because that's where I turn people who are interested in geology, I'll turn them into time travelers, okay? So we learn about the ancient past. If you learned about the processes here, you learn about the ancient past, how those processes have impacted our history. So anyway, I'll see you. You can come by and see me sometime, okay? So maybe I can get to meet you at some point. Thanks a lot. Bye now.